Hello statistics students, this is Jamie Emigh, and this video is our discussion on section 10.1, correlation. The basic concepts of correlation first. A correlation exists between two variables when the values of one are associated with the values of the other in some way. You're often going to hear questions and discussion about a linear correlation. Okay, that's a special type of correlation, and that exists between two variables when there is a correlation and the plotted points of paired data result in a pattern that can be approximated by a straight line. I'm going to show you some examples at the bottom of this slide. Some new notation though for us. This one right here is new. That's the Greek letter rho. It's a lowercase. And we're going to use that to represent the linear correlation coefficient for a population of paired data. And then a lowercase r, we're going to use that to represent the linear correlation coefficient for a sample of paired data. So they both represent a linear correlation coefficient, but one is for the population and one is for the sample. And you guys have seen that a lot in this class. For example, if you're talking about mu and x bar, both of those represent a mean, but this one here, mu is for the population, and this one here, x bar, is for the sample. So same thing with rho and r. Those are paired together if you want to think about it like that. Okay, your lowercase r will always be a value between -1 and +1, and it could be equal to -1 and +1 as well. And what this number, this r, measures is how well the paired sample data fit the straight line pattern. Okay, the closer r is to -1 or +1, this is key, the stronger the linear correlation. So if you picture these on a number line, here's your -1 and here's your +1. Lowercase r is somewhere between there, so it can be -1 or anywhere between. And the closer it is to either the +1 or the -1, the stronger the correlation. So just want to point out, 0 is right in the middle. So if your r equals 0, that would be the weakest linear correlation, because 0 is the furthest away from +1 and -1 in that shaded region. So we'll talk about that more if that's not sinking in quite yet. Okay, here is a nice visual on a positive correlation. We have r equals positive 0.81. Okay, so that's getting close to the +1, and so the r represents its strength. So how well does it fit the straight line pattern? And I could see that that fits the pattern pretty well. Like if I drew one line to try and capture all that data, or maybe more like this. Nonetheless, we call it the best fit line. And it looks like we could probably draw one line to somewhat describe the relationship or the correlation between those two variables. And what I mean by those two variables are the value on the x-axis and the value on the y-axis. So it looks like in this one, as your x value increases, so as we go this way, your y value also increases. And so each one of these data values shows that. All right, let's look at our next visual. So we've got our same two variables. We have the x-axis and the y-axis. And this time it looks like as our x values increase, our y values are actually decreasing. So if I go to here on the x, up to here on the y, then I go further on the x and lower on the y, further on x and lower on y, further on x and lower on y. You see that, how it's creating a straight line pattern? So the best fit line maybe looks something like that. So this is a pretty strong correlation. Well, how strong is it? We measure that strength, or how well, by the letter lowercase r. And for this one, that lowercase r is -0.965, which is very close to -1. So I want you to look at A and B here. This is A and this is B. And please notice that in A, we have what's called a positive correlation, and that's because our slope is increasing. And in part B, we have a negative correlation, and that's because our slope is decreasing. Let's look at two other scenarios. Here we have scenario C, and this is the one I was talking about with the R equals 0. So if that wasn't making sense, here's the visual for you. If your R equals 0, that is the value on the number line the furthest away from +1 and -1 in that shaded region. So look at the data values here. As X changes, Y doesn't really react in any type of pattern. If I go to X here, I could be here on Y, but I could also be down here, be up here, down here. There's really no correlation at all, which is fine. It doesn't mean that's inaccurate or it's graphed wrong. It just means as far as a correlation, there isn't one. R equals 0. Let's look at scenario D. This is an interesting one. As X is increasing, Y is also increasing, or at least it appears, until all of a sudden on the other side of this peak, Y starts to decrease as X increases. There is a correlation between these two variables, X and Y, but it is not a linear correlation, okay? So you can see that lowercase r equals -0.087. That's pretty close to 0 on the number line. And even though this is forming a parabola, so it has a quadratic relationship between the two variables, it does not have a linear relationship. I like to just think of it as spelling out the word linear. The first 4 letters spell the word line. So if you're asked about a linear relationship, make sure you're addressing the line versus two variables that may have a relationship like an arch, but still a non-linear relationship. Okay. So if we are asked, just in general, is there a linear correlation? And they don't specify, is there a positive correlation or is there a negative correlation? If they just ask, is there a linear correlation? Well, that means we could get very close to +1 or we could get very close to -1, which means we would have to do a two-tailed test. So to set the two-tailed test up, we use 2 capital H's, which you guys are used to, sub naught and sub 1. Your variable this time is going to be rho, because they're asking us about a correlation, and we're going to have it equal to 0. And let me erase my circle there because it covered up the does not equal sign, which is important. Your alternative hypothesis would be does not equal to 0. Okay, requirements. The sample of paired XY data is a simple random sample of quantitative data. Approximate straight line patterns exist when you graph it, and the outliers must be removed if errors, okay? And if those requirements are met, we can use a new program. You guys have seen it on your technology or graphing calculators before. It's called LinRegTTest. It stands for Linear Regression T-Test. And you'll find that by hitting Stat, Edit, you'll enter your data there, and then actually you'll find the program by hitting Stat, Test, and scrolling down to Linear Regression T-Test. Okay, I like this visual. It puts everything we've talked about so far together for us. We've got that number line with the +1 and the -1. We've got 0 in the middle. And notice that everything close to 0, if your R lies close to 0, then we're talking no correlation. But let's say your R passes the critical value and makes it into this region or this region. That's when we're going to be able to say, okay, we have a correlation. So we will set our critical value based on R. That's going to like set that bar. Then we'll find our, we used to call it a test statistic. So it's the same here. You find your test statistic from the data. And right here you can see it as sample data, R equals 0.591. And this particular R fell right here. So it didn't make it into this correlation region, I'm going to call it. You've heard it called like the rejection region a lot. Here we're talking, this is the correlation region. Well, our sample data gave us R equals 0.591, which lies right here, which means no correlation. Okay, hopefully that visual pulls it all together for you, at least what we've discussed so far. If you are asked more specifically to find if there is or is not a positive linear correlation, then you would perform a right-tailed test, because we'd only be addressing, well, let's say this part of the graph, the right tail. And similarly, if you are specifically asked is there not a negative linear correlation, then you would do a left-tailed graph, because you'd only be addressing this part, the negative. But like I said at the very beginning of this slide, linear correlation in general, two-tailed, because it doesn't matter if R is close to +1 or -1, the closer it gets to either of those, the stronger the linear correlation. All right, let's try this example. Use the paired data below to find the value of the correlation coefficient R. Is there a linear correlation between shoe print length and heights of males? Okay, we have two variables here. We have shoe prints, and these are measured in centimeters. And then we have the heights of the corresponding male. So this is one person, but two variables from them, their shoe print length and their height. And then a second person, third person, fourth person, and fifth person. And we gathered two variables from each of them. X is the shoe print length, so let's put an X right there. And then we can see on the graph here, we're gonna use Y as the height. Okay, so requirement check. We have a simple random sample of quantitative data. The plot appears to roughly approximate a straight line. We only have 5 dots, but I could maybe do a line like that, and it would show that as X increases, Y also increases. And we don't have any outliers. So we can proceed with our test. So I want everyone to set up your null and alternative hypothesis using rho, equal sign, does not equal sign, 0, and 0. Okay, it's time to pick up our technology. We're going to run the linear regression t-test. Let me delete that. That was a snapshot of the output screen. So let's do this together. Everybody go to Stat, Edit, and enter that data. So in list 1, I'm going to put 29.7, 29.7, 31.4, 31.8, and 27.6. In list 2, and I have to make sure they're paired up, okay? I'm going to put 175.3, 177.8, 185.4, 175.3, and the last one, 172.7. Okay? All right. When you're ready, the next thing you'll hit is Stat, followed by Tests, and scroll down to where it says Linear Regression t-test. It's option F on my calculator. I could have got there faster if I scrolled up. It's almost the last one. Okay, so I'm now going to run the linear regression t-test. Okay, so I open that program, and it prompts me, where did you put your X list? And I have list 1 there already, it defaults it. Where did you put your Y list? Mine defaulted to list 2 already, that's nice. My frequency is 1, and my rho we're saying does not equal 0. Make sure that does not equal sign is highlighted and calculate. Okay, there is a lot going on that output screen. If you ran it correctly, this is what you should see on your calculator, okay? A lot going on. So let's break down a little bit of the output screen. This first part right here, y equals a plus bx, that may look familiar to you. It's the equation of a line. You probably learned it as y equals mx plus b, where the value in front of the x represents the slope and the additional coefficient represents the y-intercept. Okay, the next thing we'll be using, oh, it looks like they are already arrowed down. Okay, on my calculator screen right now, the next line is t equals 1.269858246, okay? But if I hit the down arrow, now I have p equals 0.29368632226. Hit the down arrow again. I have degrees of freedom equals 3. Hit the down arrow again. I have a equals 125.4. So that's the y-intercept. Below that, now this display is caught up with my calculator, probably yours too if you're using a similar calculator, is b equals 1.727 and so on. And that is our rate of change. Then we have lowercase s is standard deviation. We have r squared, that's variation. And then at the very bottom, we have the r that we were asked to find, 0.5912690853, and so on. Okay, so that is the strength of our linear correlation. It's 0.591. Okay, so if we were to use the critical value method, they didn't specify which method, so I'm going to show you both right now. If you want to use the critical value method because you're more comfortable with that one, then you're going to compare R and the critical value. Okay, to do so though, you're going to have to use the table. CV is on the table, and it'll populate for you. Anytime you're doing a question like this, the table will populate. It's very simple table to read. All you do is go to the intersection of your sample size, which is 5, because if you recall, this was the data off of, from 5 males, and your alpha, which is 0.05, and if you recall, that's the default, and the question didn't specify us to change it. And so from that table, you'll get 0.878. That's your critical value, and that's from the table, which will populate every time you do a question. It'll be a little icon and you'll click on it. Okay, you're going to compare your critical value to your R, and it looks like R is less than our critical value, 0.878. Okay? Contrary to the p-value, not contrary necessarily, just different from the p-value, in the p-value method, we're comparing the p-value and the significance level. Okay, on your calculator screen, arrow back up. We zoomed past it. It was p equals 0.293. So this right here is also from your calculator. Significance level is the default because they didn't say otherwise. And most of us are more comfortable with the p-value method at this point. So say the little rhyme to yourself, which is p is high, the null will fly. And so we will fail to reject the null hypothesis. And then we will, whenever we say fail to reject, we always pair that with there is not sufficient evidence. And we will say to support the linear correlation between shoe print lengths and heights of people. P-value method, nice. The rhyme is super helpful. Critical value method, let me just draw the visual because I feel like it could still be easily misunderstood. We've got the negative one here, we've got the positive one here, we've got 0 in the middle, and the critical value, as you guys recall, you guys know this, it sets the rejection region. or remember, we're going to call it the correlation region. So that is at 0.878. That's our critical value. And our test statistic, R equals 5.91, it landed right about here. Oh, this is the same graph from that last slide. So if my writing isn't nice and clear for you to read, which is understandable, look at that last slide and you can see that our R equals 0.591 falls in the, going back to it, right there, no correlation region. So that supports our conclusion that there is not sufficient evidence to support a linear correlation. Okay, R squared variation. In correlation problems, R squared is used to explain that variation. For example, R squared is the amount of variation in Y, that's variable Y, explained by the linear relationship between X and Y. I'm going to say this exact statement again, except instead of the general form, I'm going to use the shoe print example. So it would read like this. R squared is the amount of variation in, and remember Y was heights. So R squared is the amount of variation in height explained by the linear relationship between shoe print length and height. Okay. It is easy to calculate. You just take whatever R equals and you square it. And actually the output screen on linear regression t-test gave it to us, 0.349. And we interpret that, okay, it goes right here. We interpret that as, we conclude that about 34.9% of the variation in height can be explained by the linear relationship between lengths of shoe prints and heights. Okay? And we just, so you'll notice you just move the decimal place twice because we're taking it from a decimal to a percentage. And then the rest of this line came directly from there. There are some common errors involving correlation. The number one, keep an eye out for this, okay? You want to make sure you understand this. It's important to understand this. It's called causation. And that is that it is wrong to conclude that correlation implies causality. So as the statisticians, we can say that one thing is correlated to the other. One variable is correlated to another variable, but we can't say that one variable causes the other variable to react in any way. So it's important to make sure you say, we support or we fail to support a correlation between two variables, not make any statements about content that we are not the experts on, and then therefore try to say something like this variable causes the other variable to adjust. Averages. You guys are going to see this too because it's also very important. Averages suppress the individual variation and therefore can inflate the correlation coefficient. So what's important to know is don't check for correlation between averages, okay? You want to check for correlation between individual data values, but don't take a whole list of X values, find the average, then a whole list of Y values, find the average, then see if there's a correlation between those averages. And last one, linearity may be a relationship between X and Y when there is no linear correlation. And that's just like that parabola I was talking about. So it's a common error, and it's important to point out and look out for. You can say that there's a relationship between X and Y, but it may not be a linear correlation. So keep an eye out for that as well. Okay, and that will end our discussion on section 10.1. See you next time to discuss section 10.2 on regression.